So the last thing I want to talk about in this section on separability is the primitive element theorem, which I think after all that we have done comes as a bit of a surprise when you first see it. It says that if you take a finite separable extension, then K always looks like f adjoin a single element. So let K over f be a finite separable extension. Then there exists some gamma in K such that K is obtained by adding gamma to f. So we wrote down plenty of extensions which were finite, of rational numbers, let's say, but which were obtained by adding a bunch of elements. Like this one was extension of degree 4, or we looked at the splitting field of x cubed minus 2, which was obtained by adding a cube root of unity and a cube root of 2. This is degree 6 extension. We are saying that all these can be written as q adjoin a single element when you choose that element judiciously. So for example here, you can check rather easily that this is same as q adjoin root 2 plus root 3. Because once you add root 3 plus root 2, you also add 1 over root 3 plus root 2, which when you multiply by the conjugate, you get same as root 3 minus root 2. And once you get root 3 minus root 2 and root 3 plus root 2, you get 2 root 3 and 2 root 2. But the rational numbers are already there, so you get both root 2 and root 3. So that's the kind of thing we are saying. And the proof is rather nice. I want to go through it. You have to make different arguments, the way I do it at least, when f is finite versus when f is infinite. So when f is finite, it actually follows from some structure result of finite fields which we did not prove. We quoted but did not prove. So assume f is finite, then K is also finite because it's a finite dimensional vector space over a finite field. Then this is the theorem that I'm referring to. The multiplicative group of a finite field is cyclic. So if you just add that guy to f, you're of course going to get all of K, because just taking the powers of that element gives you all the non-zero elements of K. So in this case, it's rather straightforward. So let's assume f is infinite. And there's an immediate reduction by induction that you only need to do this when K is without loss. We can reduce to the case when K is f adjoin two elements. So if you can take some extension which is obtained by adding two elements and write it as an extension obtained by adding one element, then a general finite extension would be obtained by adding maybe 5 elements, and you can reduce the number from 5 to 4, 4 to 3, etc. by taking 2 at a time and reducing the number of generators. So I'll just say easy to reduce to this case by an induction or something. So really what you have to do is the case when K is generated by 2 elements. So assume that for some, and I want to find a gamma such that K is obtained by adding just that guy. We'll see that a gamma equal to alpha plus c beta for some C in F works. So something like this, but there's a constant here. Okay. So to see this, let's give a name to the degree of the extension and let sigma 1, sigma 2, sigma n be the distinct embeddings of this extension in a fixed algebraic closure, fixing F. So I know that the extension is separable, so this degree is also equal to the separable degree. So there are n distinct embeddings of K in the algebraic closure. Then I'm just giving them names. And what am I looking for? So you have this extension of degree n. You're looking for a gamma such that this degree is also n. But this degree is same as the number of conjugates of gamma. So you're looking to make this equal. If they were equal, then this extension degree f to f gamma will be n. But if the degree is n, that's same as saying that gamma has n distinct conjugates in the separable case. So if you want gamma to look like this, n distinct conjugates. But what are the conjugates of this guy? They are just sigma I alpha plus c beta, I equal to 1, 2, 3, 4 up to n. So you want these guys to be different, meaning you want sigma I of this to be not equal to sigma j of this, meaning you want the difference to be non-zero for all I not equal to j, meaning you want this product to be non-zero. So look at this polynomial. Oops, I want to take the product over all I not equal to j. I want this polynomial to be non-zero for some c in f. That's what this says. You see, sigma I, sigma j, these are embeddings of f alpha beta fixing f, so they don't touch c. So when you take sigma I of this, it's just sigma I alpha plus c sigma I beta, etc. Okay, so you want this polynomial to be non-zero for some element of f. But that would be true as long as this is a non-zero polynomial, because this field is infinite. Why is this a non-zero polynomial? Let's just write it a slightly different way. This is same as sigma I alpha minus sigma j alpha plus x times, oops, this is an I, sigma I beta minus sigma j beta. And these sigma 1, sigma 2, sigma n are distinct embeddings of f alpha beta. So for if you take sigma I not equal to sigma j, then either sigma I alpha is not equal to sigma j alpha, or sigma I beta is not equal to sigma j beta. Because if both were equal, if sigma I and sigma j agree on alpha and beta, then they agree everywhere, because all that you have here is f, which sigma I and sigma j cannot touch, and alpha and beta. And it's generated by those. So if your field embeddings agree on both the generators, then they agree everywhere. So that means if they're distinct embeddings, then they have to be differing either on alpha or on beta, which means either this is non-zero or that is non-zero. For each I not equal to j, either sigma I alpha minus sigma j alpha is non-zero, or sigma I beta minus sigma j beta is non-zero. Which means each of these factors of this polynomial is non-zero. Either the constant term is non-zero or the x term is non-zero, so the polynomial is non-zero. And now if you take a non-zero polynomial, it can only have finitely many roots, right? So it cannot vanish on every element of our infinite field. So there, it's a non-zero polynomial cannot vanish identically on an infinite field. So there exists some C in F such that P of C is non-zero, but that amounts to saying that this product is non-zero. So if you let gamma to be alpha plus this C times beta, then gamma has n distinct conjugates. Sigma I gamma is not equal to sigma j gamma for I not equal to j. So gamma has n distinct conjugates, so f gamma f sep, which is same as f gamma f, is n. So that's the degree of the whole extension, f alpha beta to f. So f alpha beta is just f gamma. This shows how these embeddings help, I suppose. When we next go to Galois theory, these embeddings will again play serious roles.